So the next speaker will be Gabriel Cuomo from the State University of New York at Stony Brook, and he will tell us about renormalization group flows on line defects.
Okay, so thank you a lot for organizing this conference and for inviting me. Today's talk will be based on joint work with Zorko Margotsky and Avia Raviv Moshe, which recently appeared, and also some work in progress with the same people and Mark Mizei. So as the title says, today I'll be talking about line defects in quantum field theory. So what's a line defect? Let me start with a very broad definition. A line defect is just an extended excitation of the system, which effectively behaves as one-dimensional. And such a broad definition obviously admits tons of applications. Just to have an idea of what system we have in mind, there is an incomplete list. Famously, line defects are boundary interfaces in 2D systems. In particular, they've been studied a lot concerning 2D critical systems. Famously, the Kondo problem led to the development of the normalization group by Wilson. In 3D, line defects are typically associated either with phase defects or perhaps somewhat simpler impurities in quantum critical systems. So you take a material, it's made of some sites, and you replace one of the sites of the material with a different atom, for instance. And since it's extended in time, it's like a one-dimensional defect in the system. These have been studied, for instance, by Sajler collaborators since 20 years. And okay, in 4-dimensional, line defects are heavy probes, which are charged under the gauge symmetry of the group, typically. So like Wilson and Tooth lines. Formally, there are two equivalent viewpoints on line defects that I want to highlight. So you have your excitations, which is linear in the system, we say in RD. And you can think of it as an operator. So in weakly coupled description, you can write it in terms of the fundamental field, or you can set up some boundary conditions for the part integral at some point. These two definitions are somewhat equivalent, often related by duality. In 4D, they are like Wilson and Tooth lines, ways of defining lines. But there is a somewhat more fruitful viewpoint for the talk of today, which is thinking as a defect plus the bulk, defining as a new theory called that defect quantum field theory. So one way to understand this is you can think of your impurity in the material and you foliate along time directions which cross the defect. So once you quantize the system, it's clear you should think of the Hilbert space of the defect theory. This is a time called defect QFT, and semi-classically you can think as adding an action localized on the defect to your bulk action. That's just an intuition. So this viewpoint is particularly fruitful when the bulk quantum field theory has an extended symmetry. In particular, I will focus today on conformal field theories. So we know conformal field theories have an extended space-time symmetry. And then it makes sense to ask what is the maximal symmetry group that can be preserved by a line defect in the quantum field theory, in the conformal field theory. In particular, we define defect conformal field theories as those defects that when placed on lines or circles preserve conformal symmetry along the line and rotations in the orthogonal direction. This is SL2R times SOD minus 1. This is the best you can achieve. And as we're used from quantum field theory, generic defects will then be some sort of renormalization group flow connecting UV and IR defect CFTs. And because you can, for instance, have on a defect some interaction which depends on some length scales, which breaks the conformal invariance. And the question I want to address today is what can we say about this defect RG flow in general? So this viewpoint of a massive QFT connecting two fixed points is very typical for bulk QFTs, so it's natural to extend it to defect QFTs and asking what can we say about it. And okay, why is this an important question? Well, first we would like to make precise intuition that RG is irreversible, meaning the number of degrees of freedom per site. We want it to decrease under RG. And we want to decrease under RG also for theories such as defect theories that are not fully local, because defect degrees of freedom in the defect can interact through long-range interaction exchanged by the bulk. So that's why it doesn't obviously follow from bulk RG theorems. And also somewhat more practically, if we have some theory, we like to constrain the IR of the theory just on general principles. So for instance, we like to exclude defect RG limit cycles under some assumptions. And okay, so the reason I want to speak today is that we can actually do that and we can prove something rigorously. So for unitary and local defects, I'll be more precise what I mean by local defect in a moment. We will prove that there is a C function such that the defect CFT in the UV has GUV bigger than G in the defect CFT in the IR. And G is nothing but the contribution to the partition function from a circular defect on the circle. So You take the partition function of defect CFT minus the partition function of CFT, evaluate the same flat space with the defect put on a circle. IR divergence is coming from the infinite volume cancel in this difference, so it doesn't matter you're computing flat space. And the defect contribution is finite because it's on a compact circle. Additionally, we will show that this function is, there is a function which decreases monotonically in the DRG, which is called, we will call it entropy. And I want to say that these results actually generalize some earlier results, which were well known in the literature since the 90s about the G theorem in D equal 2. So the same statement applying were known for defects in D equal 2. So the main focus of today will be defects in higher dimensions, so in 2+1 and 3+1, just an idea. Okay, so this is the plan of the rest of my talk. See if there are no questions on the introduction. I'll start discussing some general properties of defect CFTs, then I'll discuss RG and how to constrain it. I'll discuss the main result and then some examples depending on time. Okay, so I promised I would tell you what I mean by local defect CFT. So local means that if I slightly displace the defect in some direction, so you can always take the defect and move it in some normal direction, the action of doing this is measured by a local operator on the defect infinitesimally, which is the displacement operator. More technically, it means that the bulk conservation equation for the stress tensor, this, is modified by a term on the defect, which is proportional to a local operator on the defect, which is the displacement operator. And this is a delta function localized on the defect, and n are the normal direction to the line. You might be a bit puzzled by this equation at the first glance because you don't see nothing like a defect stress tensor. And here I'm focusing about defect CFTs. And physically, this means that defect conformal field theories cannot localize energy on the line. Why is that? Well, we know that scaling variance demands that the stress tensor, both the bulk and the defect stress tensor, should be traceless. But the defect stress tensor for a line has only one component, so it must be 0. In fact, you can argue this even more generically for higher dimensional defects, but okay, I won't need to do that today. Also, this definition makes clear that defects for which the displacement operator is trivial, so that you are free to displace them in space, are just topological defects. And they are not always the trivial defect. They are, for instance, defects associated with symmetries or higher form symmetries. We know that those are topological. We can displace them around, and they are not trivial. So those, of course, have an extended symmetry group because there is nothing breaking the bulk or the identities. But these are very specific conformal defects. I said at the beginning, I will focus on defects on circular lines. So let me motivate that. So you might naively think that for a conformal defect, infinite straight line and circles should be related by an inversion, so by a conformal transformation. So they should be the same. But there is a small subtlety. To appreciate this subtlety, let me consider the one-point function of the defect stress tensor. So this is the general form implied by conformal invariant. So you just define it's fixed up to one number HD, which is theory dependent. And with enough supersymmetry, you can actually relate it to the energy radiated by the line. So it's also a very physical quantity. You expect it to be positive in all well-behaved theories. And so this formula implies that in D equal 2, the expectation value of the stress tensor is 0. So you see here there is a D minus 2, I've been explicit, and here there is 2 minus D, and X is equal to R in D equal 2. You have only one normal direction. But in D bigger than 2, these are a bit puzzling because even though they are covariant under infinitesimal conformal symmetry transformations, they imply something weird for the point at infinity. So if you look at the limit x to infinity of these formulas, you see that the limit depends on how far you are from the line. This might look like an innocent thing, but we know that conformal symmetry is a symmetry not of R4, but of its stereographic of RD, but of its compactification projection to SD. And this means that we should be able to identify a unique point at infinity. If the boundary conditions are not unique on the point at infinity, you might get suspicious something is going on. And this, we find indeed that something is going on. We don't fully understand, but I just want to, this is a well-known puzzle. I just want to review it because I think it's good to keep it in mind. And to see what is going on, let me consider evaluating the expectation value of a charge wrapped in the defect. So for context, what do I do normally? So if I want to compute, say, the scaling dimension of an operator, I consider topological charge wrapping the operator, which is just given by some integral on a surface of the stress tensor contracted with the Killing vector. And then this gives me the scaling dimension. So for the same thing of the line, I just consider a cylinder wrapping the line, an infinite line, and I put it at some distance epsilon. conformal invariance of the line suggests that this should actually be 0. But what we find is actually puzzling. If you take, for instance, the conformal Killing vector for dilations, which is part of this L2R group, you find something which is like infinity, which is just the infinite length of the line, so you might not be too worried about it, or more dramatically, which goes like 1 over the radius of the cylinder. So this charge is not topological, despite what you might naively expected. And it's clearly related with the point at infinity, because technically what happens is that that differential word identities, once you integrate them to make a charge, you cannot integrate by part because of the boundary condition at infinity. So this, of course, is well known since it's a Kaput's thing, and it has clearly to do with the fact that we didn't fix exactly what's going on with the point at infinity. And we don't know how to do it. We don't know if it can be done in a theory-independent way. And relatedly, you find that the expectation value on a line defect, so the partition function for a linear defect, is different from the partition function of a circular defect. And this is well known since studies of the early 2000s on the Wilson-Magaziner loop in an equal force per year. So, yeah, so question? Yes.
Thanks. Yeah, I mean, oh, okay. Yeah, I mean, if you had a circular defect on SD,
yes,
that would be well defined, right? And then what happens when you map it to the plane?
No, if you map a circle on SD to a circle on the plane, nothing happens.
No, I mean, if you map it to the line on the plane,
Well, you find that
something ambiguous, or
yes. So I mean, it's true. We don't have an exact answer, but what happens in the explicit case of an equal force super EMs is that you know, on the line you get some integrals which are kind of 0 if you integrate by part, but on the circle, yeah. Let me think. So what happens technically is that on the line there is a gauge fixing which makes obvious that all diagrams vanish once you value the expectation value of the equal force half BPS Wilson loop on a line. But somehow this gauge fixing is not allowed on the circle. So it's probably has to do with some boundary condition, the gauge fixing. I wish I had a better answer to that. But technically you see this very explicitly in diagrams. Yeah, I don't have a general answer what happens in general. So, okay, I'll talk about circular defect for this reason. You can focus on going very close to the circle to get back something which looks like a line if you want. But circles are very nice because here everything is transparent. So you take a circle of radius r in flat space, you call phi the angle, just standard coordinates. And this L2R Killing vector that looks slightly uglier, but no need to get scared, just a unitary transformation with respect to the one on the line. These are just linear combination of translation and special conformal, and these are just rotations on the circle. And all I need for today is their projection on the circle. They project to sine of the angle, cosine of the angle, and a constant. And in this geometry, if you just take a donut wrapped in the defect and you evaluate the conformal charge on it, then you find explicitly that the defect is conformal invariant, as you expect. So no issues of this sort. And technically you see it because here you're integrating a sign. Before you were integrating a conformal Killing vector was like linear. So you see that integrating a sign is good, integrating something linear is bad generally. You cannot integrate by part. Okay, so let me now discuss RG flows. So RG flows are generically triggered, or the RG flows will focus on today, by relevant perturbation. So you have a L2R symmetry on the Defect CFT, you can classify perturbation according to the scaling dimension. And you can just add one relevant perturbation, scaling dimension less than 1 means for a defect. Something like that. Now, as soon as you do that, you turn on a new possibility, the one of localizing energy on the defect. So if you call x.nu the Killing vector parallel to the defect, you now have in the word identities a contribution proportional to the defect stress tensor. Way to easily get convinced of this is that we know from Peskin-Schroeder that the trace of the stress tensor is just the beta function of the perturbation times the perturbations in perturbation theory. And therefore, the defect stress tensor will be just beta times the perturbation. If you want to be slightly more formal, you can say that if you didn't have this contribution, the word identity, you would still be able to construct all these L2R charges and it would still be conserved. So you clearly need something breaking scale invariance and special conformal, and this does the job. So, okay, the main identity we'll need to constrain RG flows is that the fact that the expectation value in the vacuum of a conformal charge drop in the defect is still 0. So now this is not because now I cannot shrink my donut on the defect and make it 0 because the defect is not conformal invariant. But I'm evaluating now this conformal expectation value in the vacuum. And the bulk, if you think in radial quantization, the bulk vacuum is conformal invariant. So one way to say it is to think that the defect defines a state in radial quantization. And this is just the expectation value of the charge between the defect state and the bulk vacuum. And the bulk vacuum is conformal invariant. Topologically, you can shrink this circle to nothing because there is nothing between and put the circle outside to infinity, still 0. It's a trivial identity. But it's not so trivial on the other viewpoint because the charge now acts non-trivially on the defect. So this is a nice identity. It's something is 0 equals something non-trivial. Before it was totally trivial. So we just need to identify what is the action of the charge on the defect and use this to find something useful, let's say. And how do you do that? Well, the standard trick in studying RG flows since well, forever, I think since the work of Seiberg on supersymmetry, probably it's not before, is introducing sources or spurion compensators. So here in particular, you promote your space-time mass perturbation to a function of space-time, or a function of space in this case. This is sometimes called a dilaton, but it has nothing to do with the string theory dilaton, just for context. So this may look like a bad idea because something which depends on space breaks also translation, so you break more symmetries. But it actually, it's obvious that a linear transformation of the dilaton compensates rescaling of M. So RG rescaling are compensated by transformation of the dilaton. So this should make very intuitive, even though I'm not proving it formally, that the action of a charge on the defect can be compensated by transformation of the dilaton, and eventually translates in saying that theories with different values of the dilaton are equivalent. And the different values of the dilaton are related precisely by non-linearization of the SL2R symmetry. So XID is just one SL2R conformal Killian vector on the circle. And this is the infinitesimal version. So this identity is very nice, and let us look at it slightly more closely. Let me in particular specify the non-trivial conformal Killian vector, not the constant one, the one which depends like sine or cosine of the angle. They are both equivalent. And physically, this identity is telling us that RG flows triggered by some mass scale or a different space-dependent mass scale, they're actually the same thing. So M or M which depends on time with this funny dependence is actually equivalent. So it's obvious that this identity should tell us something about RG flows somehow. And the way to obtain something concrete is to expand the partition function powers of the dilaton. So the dilaton must couple to the defect stress tensor. This is because it must compensate RG rescaling. RG rescaling solves the defect stress tensor before. So this must be the case. And now you can expand in powers of phi the partition function. And then you can define this equivalence order by order in phi and alpha. You find many identities, in fact, infinite number of identities. I will just need one of them. And it's quite easy to believe that something like this pops out if you use translational invariance. So you see that a 1-point function defect stress tensor integrated on the defect is equal to a 2-point function with modulated by a cosine of the distance. Okay, let me now converge towards the main result of the talk. Okay, I will now use this identity in a moment to derive the main result that I promised at the beginning. But for that, I need to discuss a bit more concretely the hero of the story, which is the partition function of the defect CFT. So I define log G to be the difference of the partition function defect CFT minus the partition function the CFT computed in flat space or any conformal equivalent manifold. Conformal equivalent means that the Weil factor should not touch the defect because the defect is not conformal invariant. It should vanish from the defect. So you can, for instance, compute it on the cylinder with the defect wrapping the equator of a sphere on the cylinder at some fixed time, or on the d-dimensional sphere with the defect wrapping the equator of the dimensional sphere. That's very nice because it's precisely where localization computations apply. So in supersymmetry. So this partition function can only depend on geometry, so it can depend on R, and on parameters on the defect, so the mass scale. It's dimensionless, it cannot depend on M times R. And therefore, it's natural that in the limit R to 0 and R to infinity, it must reduce to a pure number. And just by obvious short distance versus long distance consideration, this must be the value of the partition function, the IR defect CFT or the UV defect CFT. And it's a good characterization of the CFT. It's a pure number. This reflection positivity demands that the partition function is positive, therefore G must be bigger or equal than 0. And it's also easy to get convinced that invertible topological lines at G equal 1. So perhaps the non-obvious comment here is that if you have a topological line which is not invertible, like the Verdilne line in the Ising model in 2D, this will not have G equal 1, it will have G bigger than 1 famously. But lines associated with symmetries or higher form symmetries, they will always have G equal 1. So I've been a bit sloppy in my discussion so far of G, because I didn't ask whether G is a good quantity to look at. So in QFT, we should always take care of divergences. We should renormalize, or we should allow to add all possible counterterms compatible with the symmetries to a quantity. So for the partition function, we should always allow all possible geometric counterterms. So what are the counters that affect log G? Well, in D bigger than 2 at least, in D equal to, there is a subtlety that I can discuss if someone is interested. The only counterterm you can add, which has positive mass dimension, because you only want something that can be multiplied by some divergent, say, cutoff, is the cosmological constant. So something looks like M, arbitrary number, and integral along the defect. So this case like MR. So, okay, that's not a big deal. We can obtain a scheme-independent quantity by cooking up a suitable differential operator. And it's just 1 minus RDR on log G. This clearly does the job of killing this contribution. So no big deal. So as particular, what I said before about G bigger than 0 and G being a pure number actually applies up to this counterterm. So it applies to this quantity S here. At the fixed point, G clearly reduces to, this S reduces to the scheme-independent value of G, which is GUV, which I will denote GUV and GIR slowly. In 2 dimensions, S is actually an entropy. That's why we call it the defect entropy, because you can think of computing this partition function on the cylinder, so on R times S1. And now rather than quantizing the cylinder time direction, you can quantize in the circle direction. This means, and this is like doing finite temperature field theory. And this is just, and R is just the inverse temperature in that setup. So this is just the standard definition of the entropy. Or since I'm isolating the defect contribution to the partition function of the entropy, is the interface contribution to the entropy. This was the intuition of Affleck and Ludwig when they proposed the G theorem long ago. But in higher dimension, it doesn't have this interpretation, and it's still it is still a good C function. I will show. Okay, so now it's very easy to proceed. We just need to derive an identity for RG rescaling of the defect entropy. And this is kind of straightforward. So I first restore a background dilaton in the game. So for a constant background dilaton, dependence MR becomes MR e to the 5, because the dilaton can always compensate rescaling of the mass. It's standard spiral analysis. And now I can trade derivatives of M for derivatives of the dilaton, therefore. And the derivatives of the dilaton are just correlation function of the defect stress tensor. So physically, infinitesimal renormalization group rescaling are equivalent to lowering powers of the defect stress tensor. So I get, essentially, if I take an infinitesimal defect RG rescaling of M, I get this function, this equation here for the defect entropy. So this equation here is confusing because the left-hand side is a good observable. I said it's scheme independent, and therefore whatever I'm computing here must be a good quantity. But the right-hand side is possibly divergence because there's a 2-point function here. So you need to compute it in some regularization scheme. It's sensible to contact terms, and so like delta functions. And therefore it's highly non-obvious that this right-hand side is a sensible answer. In fact, it must happen by miracle that in any regularization scheme you compute it, this is a good answer. But it's highly non-obvious how this happens. And then more dramatically, it doesn't have any sign definiteness. But before I add a long discussion on how to derive some identities to constrain the RG flows, so it's obvious what is the trick that I'm going to use. I'm just going to plug those identities inside. And okay, this is a very simple system. So all I have to do is to replace the piece which was linear in TD with the identity I derived before. So which was this one. Okay. And now this is very nice because you get something which is proportional just to a 2-point function with a kernel which is 1 minus cosine. And crucially, this kernel vanishes at 0 distance. So this will make, I will discuss it in detail in a moment, this will make the answer very sensible. So let me stare a bit more at this formula. This is the main result of today. So please ask all the questions you need now, if there is puzzles. So this tells us that rescaling of RG, which you can think of rescaling of the radius of the circle, are related to this 2-point function times this factor here and a minus sign in front. So I said already this parenthesis as a double zero as phi1 approaches phi2. This means that the integral is convergent. There is no short distance divergence. This means that contact terms here, and the only contact terms here can be delta functions, the real delta functions, precisely are cancelled by this double zero. They do not contribute. By dimensionality, you cannot have other stronger contact terms. And this 2-point function is a connected 2-point function, and it's always positive in a reflection positive theory. And 1 minus cosine is positive by algebra. So there is a minus sign. So the right-hand side is manifestly negative. This means the defect entropy decreases under RG. And if you integrate it between R equals 0 and R equals infinity, it proves the main claim of today. GUV is bigger than GIR. So this is the result. Okay. I should add many comments here. First, I should give credit to the old story in 2 dimensions. Also, for you to make contact with it, assuming some of you will be certainly familiar with it. So in 2 dimensions, the claim GUV bigger GIR was originally conjectured by Alfred and Ludwig. And something most notably in the concept of boundary in CFTs, but also Alfred has very nice discussion, the Kondo problem related to that. And most notably in the context of string theory, something very similar to the gradient formula, which we discussed today, appeared. So Witten originally proposed it. Samson Shadasvili had some improvements over it, understood how to write in a covariant way, and there was also a very influential paper, Kutosov, Maring, and Moore in the 2000s. But it was only established, I would say, rigorously, to some extent, in 2D by Frieden and Konechny in 2003 for general 2-dimensional CFTs. And there is also information theoretic proof of GUV bigger than GR by Cassini, Salazar, Landento, Rob in 2016. Of course, the conjecture GUV bigger than GR belongs to the general class of F-theorem conjectures. So partition functions should be good C functions. And okay, so actually, I forgot I should have added reference to John Beccaria, John Biancitelli. They also explored it in some example. And it was also discussed systematically for defects in this paper, the conjecture. The main point I want to make, which I think is an interesting open question, is that there is there is a relation between the defect partition function and the entanglement entropy, but it's a puzzling relation. So we know since the work of Legowitz and Maldacena in 2013 that the contribution to the entanglement entropy from the defect is equal to the partition function minus a term which is proportional to the 1-point function distress tensor. So what you do, you compute the entanglement entropy on a sphere, and you ask what is the contribution to the defect to that entanglement entropy. So the defect you can put it on a circle inside, say. And this is the result. And in the equal to, I told you before, the 1-point function distress tensor vanishes. So in the equal to, the entanglement entropy and the defect entropy happily agree, and that's why there is a proof based on information theoretic approach of this statement. But in higher dimension, the 2 things do not agree. In fact, we expect HD positive, I said in general, based on, and there are many counterexamples, in fact, of the entanglement entropy of the defect being a good C function. So the entanglement entropy doesn't decrease under defect RG. I think it's interesting, and yeah, I think it's an interesting open question. So, okay, so the last part of my talk, we'll just deal with examples. Okay, so I will discuss only very simple examples. There are, of course, many non-trivial ones like Kondo or impurities, but I want to discuss some which is very easy today. And the first one example is a source in free theory. So the simplest way to turn on a defect is to add something integrated in the line and think of it as a source for some field. And in free theory, for a massless scalar in, say, d less than 4, such that the perturbation is relevant, the defect will look something like this. And here I made very explicit the dimension. In particular, for d equal 4, this defect operator is marginal. Okay, it's free theory, no mystery. You can compute everything. And you compute the defect entropy. the defect entropy will look like this. So we go like r to the power 4 minus d, crucially. So as you increase r in d less than 4, this factor becomes bigger. And that number CD, which depends on gamma function, volumes of the sphere, which you compute just on the free theory propagator. So this factor CD in d equal 4 is 0. And that's nice because I said it's a marginal perturbation and compatible with the gradient equation, the defect entropy cannot depend on marginal parameter. In d less than 4, it is negative. So it's plotted here in general. There is a divergence in d equal 2, but it's not physics because the limit of the free theory propagator in d equal 2 is singular. So it's not physical, that limit. But in d equal 3, if you want a physical case, it's actually negative. So this again means that S decreases under increasing R, so under RG. And you can check agreement with the gradient formula again. Again, here, the reason I want to present this example is that there is another puzzle, or perhaps a surprising fact, if not a puzzle, the fact that the limit R to infinity in d equal 3, say, S goes to minus infinity. And this means GAR equal to 0. This is compatible with unitarity because that should be G bigger than or equal than 0. But you would have expected or hoped to have a lower bound on G, which was stronger than that. Say, we normally believe such bounds should be there. And the best thing I can say now is that we believe this example is related, this issue is related with the presence of a moduli space. So as soon as you put a very little source, you kick the field so far away that nothing will prevent the partition function to become as big as you want. Or if you can estimate by dimensional analysis, if you think of putting the theory on the sphere and thinking that the only mass term, only potential term on the sphere scales like the radius. But we don't have a good understanding of it, I would say. So let me try to refine this example in a slightly more physical one. So let me now consider a bulk quantum critical theory. I said this is one of our motivation understanding these theories. So I'll just take the UN model in d equal 4 minus epsilon. So you can think the UN model is just a continuum limit of this kind of lattice system. And now you can imagine, again, think about it 2 plus 1. And you can imagine turn on a magnetic field only at a source. Again, this is the analogous of the defect I told you before, but this also tells you how you should realize it in your lab somehow. And now you can ask, what will be the effect of this source on the at the bulk quantum critical point? So in the epsilon expansion, once you tune lambda to be something like this. And what happens is that the trivial fixed point, h equals 0, is unstable towards an interacting defect CFT in the infrared. So I want to just argue that this instability is again in agreement with our result. So, okay, what happens is that you can compute in the epsilon expansion the beta function of h. So notice h will not be small, but this is not a problem because I can solve exactly the limit lambda equals 0 of the problem, as I told you before. So I can just do perturbation theory in lambda and leave h to be an arbitrary number. And there is an RG flow to a non-trivial fixed point, and you can find it in the epsilon expansion. And as promised, h is a further one. Say n is a further one. I'm not taking scalings with n. And nicely, you can compute the partition function. This is the answer. You can check it agrees with the gradient formula. And more nicely, you can check that it is negative. So again, in agreement with the theorem, in agreement with the conjecture I told you before, that as soon as you add the potential, the G function becomes bounded. There is no, again, instability. Again, it's some evidence for the idea I mentioned before. So the last example I want to discuss are RG flows in Wilson loops. There are a few examples, but the most studied one, in fact, there was a paper this morning about it by the same authors here, is the famous Wilson loop flow proposed by Polchinski and Sully between fundamental Wilson loops in unequal force superior means. So you take a Wilson loop in the fundamental, and you take a family which depends on a coupling zeta to a scalar in one of the SO6 direction of unequal force. So theta m is just unit vector pointing in one SO6 direction. So this is the expression, and this theory famously admits two fixed points, and I think we believe these are the only two. One is z equals 0, where this is a standard Wilson loop that we all learned. And the other one is z equal 1, which is the supersymmetric Wilson loop, an half BPS Monte Wilson loop. So a small taut coupling, so say in perturbation theory in the planar limit, you can study the flow perturbative in zeta. And this is not mysterious because if you rescale everything by G, you see that actually what you have here is G zeta. So it's you can expand the defect and just compute diagrams. And so, okay, This is an example you can study completely in perturbation theory. So you can study the flow exactly in Z in perturbation theory and perturbative intercoupling. You can compute the partition function, beta function, everything. This has been done in this nice paper by John Bitzitri in 2017, and check perfect agreement with our formula. So the gradient equation and the GUV bigger than GIR. Okay. So this is the last thing I wanted to say. So I'll just jump to the outlook. So, okay, the main result was today was establishing a reversibility of RG flows on line defects. So, but what I tried to point it out today is also some questions on the field, which I think are unanswered. So one I forgot to write is a more physical understanding of the issue of circle versus line defect, which I mentioned at the beginning. Is there a way to add degrees of freedom at infinity to fix it, at least in known examples, say? I think the main question still concern the relation with entanglement entropy. Entanglement entropy, we believe for all bulk RG flow, is a good C function. And we know it is for boundaries, actually, at least in the case where we have proof for boundaries. So why it is not the case for one-dimensional defects, and but it is probably not the case also for higher codimensional defects. Question which I think one should be able to answer, one could try to attack within the bootstrap, is whether there is a lower bound on the partition function. And in particular, under which assumption such lower bound exists. There's been a nice paper by Freedom Konechny and Schmikolina in 2012 exploring this for two-dimensional defects, so interfaces or boundaries. And but there they had to make a strong assumption on the spectrum of the bulk to DCFT. So they'd assume like that the lowest dimensional scalar, which is multiplet, which is not in the identity, should have like scaling dimensions going like C at large C. So something similar to the Hellerman bound. So it would be nice to explore this direction further, even just into D. A question which I think is very interesting is that I only discussed today flows which are triggered by relevant perturbation of the defects. And these are flows that you can extend on the circle. That's why we did that. But there is a different kind of flows or conjectural kind of flows that can be triggered by taking on a line and turning on boundary conditions at the endpoint of the lines. So you can imagine taking some ground state degeneracy in your quantum mechanics on the defect. It's allowed because now you have a long range interaction to the bulk. So standard theorems on quantum mechanics do not apply. And you can imagine triggering a Webton operator, which is going like to another ground state which breaks scaling invariance. And there are examples of this kind of flows in supersymmetric lines in holography. And these flows evade our theorem because they cannot be realized on the circle, and would be amazing to understand them, at least even in some examples. A more down-to-earth question that we are exploring is looking for more applications in impurities. So defects in 2D have been widely studied. There is also some literature on defects in 3D, but there are also many experimentally realizable defects, such as the one I showed before of turning on a small magnetic field on a site, which have not been fully explored, and which one could hope to use this technology with perhaps some epsilon expansion or bootstrap to make prediction for real world. And yeah, so we hope that our work can be useful in this direction. And with that, I conclude and thank you for your attention.
Are there questions for Gabriel? Yeah, so.
So the question is, did you use the unitarity in the bulk anywhere in your argument?
So I use, yeah, sorry, thank you. I use unitarity here when I said that this function.
Right, but that one I saw is the on the unitarity on the defect, right? So,
but I think you cannot have, you can have a non-unitary defect in a unitary bulk theory, but I don't think you can have a unitary defect CFT if the bulk is not unitary.
Okay, so I see. So that one is like unitarity for the coupled system then, in a sense.
Yes, so you need unitarity on both sides to have this. You might have a non-unitary defect in a bulk, of course. And then, of course, again, our discussion wouldn't apply.
I see. So is there any known counterexample in the, for example, okay, there can be multiple choices, but for example, the defect theory itself is unitary, but then when you couple to non-unitary, there is a, or something like that, or the other way around.
Well, I mean, the specification of a defect is always tied to a certain bulk theory. I mean, I don't know, to specify the same defect in different bulk theories. Without, I know there might be systems you can think of a quantum mechanics, but then the coupling to the bulk theory is unavoidably dependent on the bulk theory and your choice.
Yeah, okay, so if you include a coupling as a definition of the defect, yes. And basically, okay, thank you.
Yeah.
Have you thought about higher dimensions? Like, in other words, surface and higher?
Okay, so, well, there is already work in higher dimension. So for four-dimensional defects, there is a C theorem already proved. And the idea there is the same one of the two-dimensional, well, the 4D theorem and 2D version. Because essentially there you have anomalies in the scale invariance, and then you can do anomaly matching between IR and UV. In the case of 2D, it has been done by Jensen and by O'Bannon and Jensen. And in 4D, it has been recently done by Yifan Wang. So the only subtlety is classifying carefully the anomalies on the surface. I think the open question is 3D. There is some work by Cassini and others on some, I would say, not conclusive results, is my understanding of the work, but I'm not an expert of entanglement entropy. But yeah, I think the open question is 3D.
But sorry, I guess in general, you wouldn't expect that the entanglement entropy would be the right quantity if it wasn't already here.
Yeah, sorry, when I said the work of Cassini is 3D embedded in 4D. So for boundaries, the two things agree. So that's why it would work.
I see, yeah. One other quick question, if I may. Did I understand correctly that the notion of number of degrees of freedom on the line defect, it doesn't have a definite sign in general, right? Like it could have more than no defect and less than no defect. That's both allowed.
Yeah, I think the invariance statement is that you have flows from the trivial defect to non-trivial defects. So, well, I showed you here two examples somehow.
Right. But you could go the other way too, right? Couldn't you have a defect?
You can have some which flows to a trivial defect as well, or a topological defect actually.
Thanks.
So in principle, we have still maybe time for one quick question, maybe in the chat. It doesn't look like it, so I would say let's thank the speaker again for his nice talk.